Here's some code. It runs in 2 milliseconds on a list of 100 items. Same code, 10 million items, it doesn't take longer. It doesn't finish. That's not bad luck, that's big O. And once you actually understand it, you will never write code blind to this again. Big O isn't about speeds in seconds. Your laptop, a server, a phone, they're all different speeds. Big O is about something speed can't tell you. How the amount of work grows as your input grows. Forget the math symbol for a second. Just watch what happens to the work as the input gets bigger. Grabbing the first item in an array doesn't matter if there are 10 items or 10 million, it's the same one step. Here's the code. One operation, one loop. Run it again with a bigger array, still one operation. That's constant time. Big O of 1. The size of the input never enters the equation. This is the index trick from last video. Binary search. Take the middle and throw away half the list every single time. Look at the code. One loop, but what's the range shrink? Low, high, middle, again. Each pass cuts the problem in half. 10 items, about 3 to 4 steps. 10 million items, about 24 steps. Double the input and you only add one more step. That's what log n actually means. Checking every item one by one until you find what you're looking for. The code, one loop, one operation inside it. Running once per item, 100 items, 100 checks. 10 million items, 10 million checks. The work and the input grow exactly the same rate or straight line. That's big O of n. This one shows up constantly and most people can't explain it. Merge sort, split the list in half over and over, then merge it back together in order. Splitting in half repeatedly is our log n from before. That's the depth of the recursion. But at every level, you still touch every item wants to merge it. That's the n. Multiply them n items times log n levels. That's why most efficient sorting algorithms land here. Not an n and not an n squared. Bubble sort. For every item, compare it against every other item. Two nested loops. The outer loop runs n times. For each of those, the inner loop also runs n times. N times n. 100 items isn't so bad. 10,000 comparisons, but 10,000 items? 100 million comparisons. Double the input and the work doesn't double, it quadruples. This is the complexity class that quietly destroys performance at scale. Naive recursive Fibonacci, the classic interview trap. Every call branches into two more calls. What's the call tree? One call becomes two, two becomes four, four becomes eight. By the time n is 30, you are making over a billion calls. By 40, your program doesn't crash, it just never finishes. This is the complexity class where technically correct and actually usable stop being the same thing. Quick gut check because this confuses almost everyone starting out. If your code has a one loop and a second separate loop, that's n plus n to n operations. So why do we still call it big O of n, not big O of 2n? Because big O describes the shape of growth, not the exact count. As n gets huge, the difference between n and 2n stops mattering. They both just look like a line. Big O drops constant and smaller terms because it's answering one question. Does this scale or does it fall apart? Put them all on one graph as n grows, and this is the image to actually remember. Big O of 1 is flat, big O of log n barely climbs, big O of n is a straight diagonal, big O of n log n curves up just a little faster, big O of n square bends sharply, and big O of 2 power n, it doesn't just rise, it goes vertical and leaves the chart. One more wrinkle. The same algorithm can have different complexities depending on the input. Quicksort is usually big O of n log n, fast in practice on most real data, but feed it data in exactly the wrong order and it degrades to big O of n square. When an interviewer asks for time complexity, the sharp answer isn't one number. Its average case is this, but here is the worst case and here's what triggers it. Time isn't the only cost. Recursive Fibonacci doesn't just take a long time. Every call sits on the stack waiting on the next one, so it also uses big O of n extra memory. Compare that to an iterative version with a simple loop and two variables, same answer, but big O of 1 space. Interviewer asks for both numbers. Now you can actually give them the both. Let's actually do this code the way an interviewer would hand it to you. To sum. Given a list of numbers and a target, find two numbers that add up to it. Naive approach first. For every number, check it against every other number. That's our nested loop from before. Two loops, n times n's big of n square. Looks fine on paper. Try it on a list of 50,000 numbers and you are sitting there for a while. Better approach. One loop, but as you go, drop each number into a hash map. Before adding a number, check if target minus this number is already in the map. One loop and a hash lookup is big of 1. So the whole thing is big of n times big of 1, which is just big of n. Same problem, same correct answer. One version is quadratic, the other is linear. And the entire difference came down to trading a second loop for a lookup. That's not a trick you memorize. That's the exact muscle every scene in this video just built. So here's the actual move. Next time you are handed code cold, find the loops first. One loop is usually n. Nested loops are usually n squared. Check if the problem size is shrinking each step. That's your log n. Check if you are branching into multiple recursive calls. That's exponential territory. Then ask what the worst input would do to it. That's not memorizing 7 symbols, that's actually being able to read any code and know how it will behave when it stops being small.